Sir,
Yeah.
sir, just one. This is off the topic, sir. This is regarding the angle encoder, sir, which you taught us on chapter 4. Sir,
Yes.
actually, we are taking the compression TDC, as you mentioned, no, sir, for as a reference point, which is slightly before the actual piston TDC.
Yes.
But sir, in this two-stroke marine engines, diesel engines, we have encoders, but we take, in fact, we have two encoders, one for safety redundancy. So the first encoder, we always take at exact 0 degree TDC of the crank angle, which is the first unit at TDC. Sir. And the second encoder, we will take with an offset of 45 degrees. Basically, that is to have a difference in the references, so that even if one coder has a failure or if it has a problem, then it should not replicate the same, because the control systems are of the same circuits. So it should not have a mismatch. This reason being, every controls, that is fuel injection, exhaust valve actuation, cylinder lubrication, are all dependent on the encoder signals. That is why we always have exact 0, and the error margin allowed is also 0.02 degrees. Because if we go beyond that, then we get an encoder failure alarm. So just wanted to understand this difference in the reference TDC. Is this because of it's a slow speed engine, or it's for any other reasons? I just wanted to have your concurrence on this.
No, I don't know about why you want two reference here. So my suggestion is you can go with one reference like we discussed. For
Okay,
4-stroke and 2-stroke, the difference is you have one cycle completed in 2 strokes of the piston.
Yes.
Okay, but you see that the processes are combined in a 2-stroke. For example, when the piston moves up, you will have intake happening on the crank side and compression happening on the piston side.
Correct, sir.
And
Correct.
near the end of compression, the combustion will get started. Okay, depending on whether it is SI or CI.
Yes, sir. Yes, sir.
So then, so after the piston reaches compression TDC, that is the region where the combustion is started. Around compression TDC only, the combustion will get started even in 2-stroke engine. The only difference here is in 1 stroke of the piston, you have compression happening and you have also intake happening on the crank side.
Yes,
Compression
sir.
happening on the piston side.
Correct.
When the combustion gets started, the piston start moving down for expansion. During the same expansion stroke, you have exhaust also happening.
Yes,
so
sir.
one cycle is completed in 2 strokes of the piston. That's the only difference. Okay. But combustion process, if you look at it, is happening in the same way as a 4-stroke cycle engine, whatever we have discussed.
Okay.
My suggestion, my take on this would be we can consider the compression TDC as a reference point, same as how we have done for the 4-stroke. That 45-degree offset, why it is required, I'm not sure. Maybe I need to look at.
No, sir. Sir, for that one, actually, the control system, the networking is common for all the units, because we have minimum 6, maximum up to 14 cylinders. So when we have this control system, normally we have common engine control unit, which commands each unit, and each unit has its own control system. So when one encoder gives an error, then the system will understand for the second encoder as well as the same error. Although the second encoder is working fine. That is why we have 0 to 180 degrees for one encoder and 45 to 225 for the second encoder. And in addition to this, we will have a pickup sensor near the flywheel side. That is as a supporting reference to not only depend on the forward of the engine, rather we will have this on the aft reference as well. So that's the reason we have this encoder offset for between these two encoders, 0 and 45. But my only question was, sir, why we are taking here exact TDC? Maybe it's because of slow speed engines, sir. Because in generator engines, we don't have this. As generator engines, we have exactly as what you said, sir. That we will take the compression TDC only, sir. But only for large 2-stroke engines, we have like this, sir.
Large 2-stroke engine, your question is, we are taking 2 references. Do we have to take or not? Is that your question?
No, sir. For large 2-stroke engine, I'm saying why we are taking the piston's actual TDC, not the compression TDC.
What do you mean?
That is 0 degrees. So that means when my number 1 unit is at exact TDC, piston is at exact TDC, we take that as the reference point, sir.
And the piston is at TDC. That is compression TDC, right?
Correct, sir. Correct, sir. Correct, sir.
Same as what we discussed. Compression TDC is what is the reference. So you are starting with 0 at when the piston is at TDC, right? Compression TDC.
Yes, sir. Correct, sir. Correct, sir.
That is fine.
Okay. Okay, sir. Okay.
That is fine. When the piston is at TDC, compression TDC, you are taking that angle as 0 degree, right?
Correct, sir. Correct, sir. As a reference point, sir.
That is fine. Here also we can do that. The nomenclature generally followed is we can take compression TDC as 0. Any angle before that can be taken with a negative sign. Any angle after that can be taken with a positive sign. So sometimes we also use A TDC and B TDC, before TDC and after TDC. Okay. After TDC is written with a positive sign, angle, and B TDC is written with a negative sign, because the nomenclature generally followed is if you use A TDC everywhere, then positive sign means it is after TDC. Negative sign means it's before TDC. This is just a nomenclature, standard nomenclature, but nevertheless, you can consider piston TDC as a 0 angle.
Understood, sir. It's clear, sir. Thank you, sir.
Okay, fine. Yeah, so welcome back. So we are in chapter 5. Here we are looking at, this is the second module of this course, emission module. So in this module, the first chapter is about pollutant types, and we are also going to discuss about the sources for the pollutants. So what we have discussed so far is the engine as a resultant of combustion emit various species into surrounding ambience. Out of the various species emitted by the engine due to combustion, some of the species are designated as pollutants because of the health effects they create on the human being. Some effects are immediate and some are long term. We discuss about those effects. So 4 species emitted from the engine due to combustion are having detrimental effect on the human health. Okay, sometimes the effect may be fatal also. It depends on the concentration of the pollutants that goes into the human body. If it goes beyond a threshold limit, it can create any effect, including fatal. So that's why it's very important to keep a check on the concentration of these 4 species. That's exactly the reason why we have emission standards, and why we are checking the pollutant, these 4 species levels before a new vehicle is launched into the market. All the countries have their own emission standards, okay, based on the prevailing conditions. We have our Bharat BS standards, okay, as you know. So the pollutants are having detrimental effect on the human health. That's why it's very important to understand how these species are formed as a resultant of combustion events. So we are tracking the sources where these species are forming, and we are also going to look at the formation mechanism of these 4 species. Okay, and then we will also look at the factors, engine design or operating variables that are influencing this 4 species formation. Once we have a complete idea about the mechanism, as well as if you have an idea about the variables that influence this 4 species formation, we can adapt a suitable strategy. That is what we are going to discuss in the next chapter. So towards that, now we are spending time to track sources for the formation of these 4 species in the engine, SI and CI engine. We deal with the sources separately because the sources are slightly different for these 2 IC engine categories. That's why we are looking at separately for SI engine and CI engine. Later on, we are going to look at the formation mechanism. So this is an overview of pollutants that we have already discussed. Engine emits various species, a circle, red bubble, are the regulated or criteria pollutants, which are also primary pollutants. Okay, and we also discussed that this primary pollutants, once they are let out into atmosphere, they also start to form other species which are called secondary pollutants. Under ambient pressure and temperature condition, these 4 species are also forming other secondary pollutants in the surrounding ambience. That's why it's very important to control or keep a check on the concentration levels of these 4 species. Okay. So we have earlier discussed about the sources for pollutant formation in spark ignited engine. In spark ignited engine, okay, we have 3 species, pollutant species. NO2 concentration is generally less than 3%. Later on, I will discuss why it is low. And then you have SC, unburned hydrocarbon, and CO, carbon monoxide. These three are the pollutant species. So we are tracking the sources for this three species formation in a typical SI engine operating cycle. And we came to know that in an SI engine operating cycle, this species form during these processes that happens in an engine operating cycle: compression, combustion, expansion, and exhaust. During the compression process, we have sources for forming unburned hydrocarbon through these carbon deposits and oil layers, which can absorb or trap some of the fuel. Okay, some fraction of fuel is trapped or getting trapped in this carbon deposits and oil layer. During the compression process, when the piston compresses a fuel or mixture, in an SI engine, we are compressing fuel or mixture. A fraction of that mixture go and get locked in this deposits and oil layer. As there is also a crevice flow, which is one of the major contributor. Okay, the crevice are the radial clearances that are available between the piston and the liner. There are also crevices in the valves and the cylinder head. So these are also called as dead pockets. So in these dead pockets of fuel, a fraction of fuel will go and get locked, and this fuel will miss the main combustion event, and it will enter into the cylinder during later part of expansion stroke, where the pressure and temperature are considerably low. Thus, it becomes a source for unburned hydrocarbon. During combustion, NO and CO will form. CO forms due to oxygen deficiency, and NO forms due to high temperature burn gases. High temperature is a source for forming NO, and that happens during the combustion event. And then HC also forms during combustion event due to incomplete combustion, and the pressure in the cylinder is high during combustion. That will make a fraction of unburned fuel go and get locked in the crevice. That is also happening simultaneously. During expansion, the NO and the CO kinetics will stop because of drop in temperature. As you know, during expansion, piston moves down. There is a volumetric expansion that will result in drop in temperature in the cylinder. Drop in temperature will stop the kinetics. First, NO kinetics will stop. Subsequently, CO kinetics will stop. Okay, and then since the pressure and temperature drop considerably inside the cylinder during the later part of expansion stroke, there will be backflow of the unburned mixture from the crevice region to the cylinder region. So by this time, the pressure and temperature are considerably low. Because of that, the unburned hydrocarbon cannot get oxidized, and thus it becomes a source for HC emissions. Exhaust, during exhaust period, the carbon deposits and oil layer will release the unburned hydrocarbon. It's a desorption process. So the trapped hydrocarbon here refers to unburned fuel. So this will be released into surrounding, in the cylinder during the exhaust process. Since the exhaust valve is open, this hydrocarbon, unburned hydrocarbon, will leave along with the exhaust gas. So in summary, as we have seen, NO and CO are formed due to kinetics. NO primarily governed by high temperature, CO primarily governed by oxygen availability. But nevertheless, these two processes are kinetically controlled. NO, CO formation processes are chemical kinetically controlled processes. Whereas SC is slightly different compared to NO and CO. This is primarily governed by boundary layer fluid dynamics. It depends on the flow of mixture, unburned fuel or mixture into the crevice region, which is a major source. It also depends on the flow of unburned fuel or mixture into the oil layer, lubricating oil layer, as well as carbon deposits. So all these are happening in the boundaries of the combustion chamber. That's why we say that the concentration of HC in the engine exhaust is dependent on the boundary layer fluid dynamics, how the fluid flow happens into the oil layer or carbon deposit or the crevice. That is what is going to decide the total final concentration of HC that leaves along with the exhaust gas. Okay, so HC is based on fluid dynamic, boundary layer fluid dynamic, and NO and CO are based on the kinetics. After that, we get started with tracking the sources for CI engine pollutant. In CI engine, we have 4 pollutants. Okay, unlike SI engine, we have 4 pollutants, and in NOx, NO2 concentration is also high. It can be as high as 30%, and the remaining is NO. So we have more pollutant species emitted from diesel engine. That's why I say that pollutant control is somewhat complex or challenging in a diesel engine compared to spark ignited engine. So here the fuel is injected near the end of compression stroke. We give a very less time for fuel air pre-mixing before the combustion gets started. This less time for fuel air pre-mixing leads to heterogeneous or non-uniform fuel air mixture inside the combustion chamber, and that's why you have this phi local different from phi global. So we have two equivalence ratio. As you know, global is always lean. In a diesel engine, we use up to 30 to 50% XSR. And we know that the operating phi range is 0.4 to 0.8. But the local value is not equal to this. Local value can be anywhere between 0 to infinite. And that is primarily due to heterogeneous mixture inside the combustion chamber. So this local equivalence ratio is a function of space and time. So this is a function, the value, phi local value is a function of space and time. Space here refers to the location inside the engine cylinder, combustion chamber, and time in terms of crank angle. You are going to have different values of phi local. Phi local is not equal to phi global because of heterogeneous mixture in CI engine, whereas in SI engine, you have a homogeneous combustion. So the local phi and global phi are going to be same. This is one of the major difference that governs pollutant formation in these two engine categories. In fact, this is the reason why we have more number of pollutant species in a diesel engine compared to SI engine, and this is exactly the reason why pollutant control is challenging in a diesel engine compared to spark ignited engine. So the pollutant, this four species formation in a diesel engine depends on how the mixture distribution varies with respect to time. That is what is going to govern the formation rate of these four species, how the mixture distribution, that is how the local equivalence ratio vary with time. That is what is going to primarily govern the formation rate of these four pollutants. Okay, so NO, similar to SI engine, NO here also is formed in the high temperature bond gases. Okay, but only difference here is you have a different global and the local equivalence ratio. The local equivalence ratio distribution is what is going to affect, because you know NO forms with high temperature, and high temperature also is dependent on the equivalence ratio inside the cylinder. Okay, so the temperature will be high only at certain equivalence ratio, and equivalence ratio also decides the oxygen availability. Okay, so based on how the mixture distribution is happening locally, how the local equivalence ratio varies, the temperature, local temperature is going to be dependent on. Accordingly, the NO formation is going to be dependent on that. That is how it differs from SI engine, wherein you have a uniform phi, uniform temperature, and generally it is high in SI engine. Okay, so NO concentration or formation again is kinetically driven based on high temperature, but here we use the word local high temperature, local equivalence ratio are the deciding factors for the final NO concentration. CO is formed in fuel rich zone wherever you have oxygen deficiency. In fuel rich zone, you know that oxygen availability is less, and that is what is causing the partial oxidation of carbon in the fuel. CO is due to partial oxidation of carbon in the fuel. Okay, complete oxidation will lead to CO2. Wherever you have less oxygen, you will have only partial oxidation of carbon. So carbon present in the fuel will get into CO rather than CO2. So fuel rich zones or oxygen deficiency is a source for forming O2. This is similar to what we have discussed for spark ignited engine, but again the difference is you have a local equivalence ratio distribution that is happening in a diesel engine. This is a governing factor for the total CO that is formed in the CI engine. HC, the sources are slightly different compared to spark ignited engine. Okay, in compression ignited engine, the SC sources are primarily governed by the mixing. So when you have overlean region inside the combustion chamber, overlean regions are primarily due to over mixing. When fuel and air, when air is mixed too much with the fuel, you will have a high air concentration with very less fuel concentration. That will lead to equivalence ratio below the lean flammability limit. So you know there is a ignitable range of phi. Okay, so you know there is a phi ignite, phi that is ignitable. Okay, this is also called flammable range of phi. Okay, there is an upper limit, there is a lower limit. When I say lower limit, it is on the lean side. When I say upper limit, it is on the rich side. So there is a range of phi that fuel air that you can burn, you can ignite. What will happen due to over mixing? There will be regions with very lean in the sense too much of air, very little fuel concentration. Okay, it is below the lean flammability limit of the Phi value for the given hydrocarbon air mixture. That's why you will have this hydrocarbon, unburned hydrocarbon formed with those mixtures. There is no complete oxidation because it is below the lean flammability limit. There may be partial oxidation leading to forming HC. The other source is undermixing. It is just opposite to what we have discussed about over lean region or over mixing. When the air is not mixed well in region, you will have high fuel concentration with less oxygen concentration. This is what is I mean by undermixing. So you will have Phi value beyond the rich flammability limit. There is a lean, there is a rich limit. Okay, when there is undermixing, the Phi value will be very high locally. This very high Phi value will result in unburned hydrocarbon emission because the fuel cannot completely oxidize. There may be only partial oxidation or it may completely miss the oxidation. So it leads to HC formation. The other source is spray impingement on the cylinder wall. So when you spray fuel, we know that in a diesel engine, we are spraying fuel at a high pressure. Since you are spraying at a high pressure, the pressure varies anywhere between 300 to 3000 bar. Okay, so there is something called a spray penetration length. There is something called a cone angle. So this is an cone angle, and this is a maximum penetration length. Okay, in an axial direction, and so it can go up to some wall. You know, this is a cylinder wall region. You are circulating coolant here. So this is a region with the lowest temperature in the combustion chamber. So the temperature here is considerably low. When the fuel go and hit the wall, it will form a film. Okay, so this is fuel film. So you will get into forming a fuel film around the wall region. When the fuel forms a film, what problem will be encountered in terms of HC formation? So here also on the other side also you have coolant. Okay, so this is a wall region. So it may form a film. What problem will be encountered if the film is formed, fuel film is formed?
It will increase, sir. The SC will increase.
SC will increase. We already discussed about the mechanism of fuel vaporization mixing. Okay, if you recollect in the very first chapter, the mechanism should be something like this. So when the fuel is sprayed, the outer periphery will be broken. It will be like a film initially. Because of air resistance, the film is broken. Okay, the air is offering shear force. Okay, due to the shear force, the outer periphery of the fuel spray will start to break and form drops. So the drop formation has to take place. Without drop formation, the vaporization is very difficult. Considering the time scale involved, time scale is typical microsecond or millisecond. Okay, at the most millisecond, microsecond or nanosecond. It may also be nanosecond depending on the engine running speed. So the drop has to form. If there is no formation of drop, if the fuel is forming a continuous film, the problem is air cannot entrain. Until air entrain, there is no vaporization because the latent heat of vaporization for converting liquid phase fuel to vapor phase fuel is obtained from air. Air is providing the latent heat. So latent heat of vaporization is provided by air to the fuel. Air is at a high pressure and temperature when the fuel is sprayed. Okay, so typically I have given some number also. It's around 30 bar and around 700 to 800 K. Okay, air is providing the fuel film. When the air is providing the latent heat. When the fuel go and hit the wall, the problem is the temperatures are low on the wall because you are circulating coolant nearer to the wall. The temperatures are less. Okay, and the other thing is you are having a continuous film. The drop formation is very difficult. The drop formation is easier here because air is offering a shear resistance, right? Shear force. The shear force is helping in breaking the film into drops. Whereas in the liner region, in the liner region, it's very difficult to form drops, similar to here, what is happening in the core region. Okay, so this film will take longer time for its vaporization. Okay, it may take more time than the engine cycle time. Did you understand what I'm saying? Once the film is formed around the wall region, sometime this film vaporization will take longer time than the engine operating cycle time. Because of considerably higher time taken, the vaporization is going to happen slowly. It may get into other cycle also, next subsequent cycle. And slowly it vaporizes. It may also vaporize during the exhaust stroke where the exhaust gases are leaving. Right. So when this fuel slowly vaporizes, this vaporized fuel is going to be taken along with the exhaust gas. Thus, it becomes a source for unburned hydrocarbon emission. Spray wall impingement is a problem in diesel engine because of the reason that you have a high pressure injection. Under certain conditions, the spray may go and hit the wall. The problem is severe in small bore diesel engine. When the diameter or the bore, cylinder bore is less, when this is less, you can expect a higher flame spray wall impingement. Clear? So this is one of the source, spray impingement on the cylinder wall, fuel spray impinging on the cylinder wall and vaporizing slowly. That becomes one of the source for HC emissions. And then you also have another source in terms of fuel collected in the nozzle sac volume. There is something called nozzle sac volume. This sac volume is a small volume provided at the end of the injector. If you look at the injector tip, the tip of the injector consists of this sac volume. This sac volume is provided for two reasons. One, it provides a surface for the needle to go and sit. Okay. So it provides a seat for the needle. So needle, you know, it's normally in a closed position. Whenever you actuate this needle, it's going to lift and it is going to allow the fuel spray to get into the cylinder. Otherwise, it remains closed. So this sac volume provides a surface for the needle to get seated. That is reason number one. Reason number two, around the circumference of the nozzle sac volume, you have these orifices. So you will have n number of orifices depending on the requirement of the total fuel that is to be injected into the engine cylinder. So it may be 3-hole injector, it may be 5-hole, 7-hole or 9-hole injector. The number of holes are dependent on several considerations. It depends on the power rating and how much of fuel you are going to inject. Okay. So this provides a surface for measuring orifices. You will have n number of orifices are located around the this sac volume in a radial direction at equal angular intervals generally, because we want to ensure that uniform air availability for all the spray. Okay, you have to have a uniform mixture distribution. So you need to ensure that the air availability is equal for all the spray. That is one of the important consideration. So for this reason, we have a sac volume. The problem with the sac volume is once you allow the fuel through the sac volume, only the spray is getting into the engine cylinder. What will happen after the duration of injection is over? The needle will go and sit, okay, in its place as shown in this simple schematic. Once the needle sit, the fuel that is collected in the sac volume, okay, there is some volume of fuel getting collected based on the sac volume. Okay, based on the volume magnitude of the sac volume, there is some fraction of fuel getting collected in this region. And this fuel, once the needle sits, you know the pressure is lost, right? You don't have any high pressure. Once the needle sits, the high pressure region is closed. So the collected fuel will get into the engine cylinder at a lower velocity. This is where the problem is. Since the pressure is lost, you have fuel. We use the word dripping. The fuel will start to dripping or leak through the orifices slowly at a very low velocity because high pressure is lost. Once the needle sits, the high pressure is lost. So the collected fuel in the sac volume start to drips out through the orifices into the engine cylinder. And since they move at a low velocity, they get into cylinder at a low velocity, you will have a problem of creating a mixture with this low velocity fuel that is dripping into the engine cylinder. We want fuel to enter at a high velocity. Because of this, we have a high injection pressure, right? The fuel should be sprayed at high pressure so that you have a high velocity. This high velocity helps in increasing the relative velocity between fuel and air. That is how mixing is better. Now, if you have a fuel dripping out at a very low velocity, you can imagine what will happen to mixing of that fuel with air. Mixing is going to be very poor, and thus it becomes a source for unburned hydrocarbon emission. The fuel collected in the sack volume enters into combustion chamber at low velocity. Because of that low velocity, it creates problems related to mixture distribution, and finally we end up in having that as one of the source for unburnt emission. Okay, so that is how HC gets formed in a typical diesel engine. Then we have this PM, particulate matter. Particulate matter is emitted only from diesel engine, not from SI engine. Diesel engines emit this due to heterogeneous mixture, as we have just now discussed. I will give more detail about the composition of particulate matter, but just take a note here that the particulate matter is one of the most complex pollutant emitted from IC engine. It's one of the most complex pollutant. Why I say most complex pollutant is the composition of the particulate matter, or we can say that the particulate matter is not well characterized even today. Even today, we don't know the exact composition of the particulate matter. Some of the species are unknown. Okay, so that's why I say that this pollutant, particulate matter, or simply particulate, is one of the most complex pollutant emitted from IC engine. It consists of all three states of matter. So this include solid, liquid, gas phase. All three states of matter are present in this pollutant. Everything put together is pollutant matter. The major component is soot. Soot is a solid carbon. Solid carbon is what is soot. When we are burning hydrocarbon fuel. The hydrocarbon fuel, when hydrogen content is removed, if you have a very high carbon concentration, then it leads to soot. Soot is nothing but solid carbon particle. It's a solid phase matter. Okay, so we have a solid phase matter. We also have something called the soluble organic substances. Soluble organic substances, the source is fuel and lubricating oil. So here we have from, this is from fuel and lube oil. Fuel and lube oil leads to forming the soluble organic substances during combustion even. And when you have a solid surface, soot particle surface, the particle will carry these organic substances, and these are liquid phase. These are in liquid phase. Soluble organic substances are in liquid phase. So you have a liquid phase matter in the particulate matter in terms of soluble organic substances. And then you have inorganic substances. Generally, they are in the gas phase. Okay, it refers to something other than carbon and hydrogen. That is what is inorganic. In an engine context, it will be nitrogen-based oxides and sulfur-based oxides. They are put together as inorganic substances. So you have a solid matter, you have a liquid matter, you also have a gas phase matter. Everything put together is particulate matter. Okay, the primary component is soot. If you could control soot formation, then you can avoid this other two. Okay, so the target for controlling particulate matter should be on the soot. We should avoid excessive soot formation, otherwise you will have these other substances getting through the soot, and then it will be let out into atmosphere as a everything put together as a particulate matter. This is what is being emitted from diesel engine. The formation of soot is due to heterogeneous mixture. The ideal equivalence ratio range is 2 to 4. 2 to 4 is an ideal equivalence ratio range that helps in forming very high levels of soot. Okay, so if you avoid this, then soot concentration will be reduced in the engine, and the other two comes as a subset of this soot, because soot is what is providing surface for carrying the soluble organic substances and inorganic substances. Okay, so we should primarily target to control soot if you want to control the particulate emission. Okay, but particulate emission primarily includes soot, and that is primarily due to heterogeneous mixture with the equivalence ratio local value in the range of 2 to 4. This soot forms over a wide range of pressure and temperature. I'm going to give more detail about formation mechanism of soot later on. But here just take a note that the soot is formed due to fuel-rich mixture in the range of 2 to 4 over a wide range of pressure and temperature. Once soot is formed, it provides a surface for carrying this liquid particle and gas phase substances. Clear? These are the sources for pollutant formation in diesel engine. So we have understood the sources for pollutant formation in spark ignited engine and diesel engine. In spark ignited engine, we have SC, CO, and NO, three pollutants, and in diesel engine, we have SC, CO, NOx, NO and NO2 together, and then we have particulate. We understood the sources for this species formation in SI and CI engine. Next, we are going to discuss the mechanism, formation mechanism of this species. Okay, starting with the NOx. So now we are going to start with the formation mechanism for NOx. NOx is oxides of nitrogen. When I say oxides of nitrogen, it can be any oxide, but in IC engine context, we have only two oxides. One is NO. NO is nitric oxide, and the other one is NO2. NO2 is nitrogen dioxide. These two oxides put together is called a NOx, which is one of the objectionable pollutant. Its health effects we have already discussed. Out of these two, in SI engine, the NO2 concentration is very low. It's negligible, less than 3%. Whereas in a diesel engine, it can go as high as 30%. The general range, typical range is 10% to 30%. The rest is NO. 10% to 30% is NO2. Later on, I will, through the mechanism, through the discussion on mechanism, we will understand why NO2 is low in SI engine, it's high in CI engine. For that, we need to look at the formation mechanism. So that's what we are going to see now. First, let us look at the NO formation mechanism. There are three routes. We call it as routes or ways by which NO, nitric oxide, is formed in the IC engine. Okay, both SI and CI engine. So one of the route is called thermal NO. Other one is prompt NO. Third one is fuel NO. So there are these three are the routes or ways by which NO is formed in a IC engine. Out of these three, NO formed through the thermal route is significantly high. You could see that 90% of the total NO formed from IC engine is through this route, thermal NO route, right? And the source for forming thermal NO is high temperature bond gases. High temperature bond gases provides a source for forming thermal NO, and its contribution is 90% out of the total NO formed in IC engine. Prompt NO contribution is around 5 to 10%. So this is formed, the contribution of prompt NO is around 10% at the most, max value is around 10%. And this is the NO formed within the flame front. Within the flame, some concentration of NO is formed. So here thermal NO, I refer to NO formed in the bond gases, high temperature bond gases. That is a region where thermal NO is formed. Prompt NO is formed within the flame. So you know we have a thin flame. Thin flame. We are talking about NO formed within the flame. This is what is prompt NO. So this is a flame, typical flame, and prompt NO is a NO formed within the flame zone or chemical reaction zone, and its contribution is around 10%. Why it is such a low value, we'll discuss. Third source is fuel NO. So fuel NO is due to oxidation of nitrogen present in fuel. Thermal NO and prompt NO are due to oxidation of nitrogen present in air. So you know air has nitrogen and oxygen, major component. Oxygen around 79%, nitrogen around, oxygen around 21%. And nitrogen around 79%. Okay, 79% nitrogen is available in air. Oxidation of this nitrogen present in air at high temperature is what is causing thermal NO and prompt NO. Whereas the locations are different. Thermal NO, it's formed in bond gases, high temperature bond gases, and prompt NO is formed within the flame region, flame zone, chemical reaction zone. Locations are different, but the source is air. Air has nitrogen around 79%. Oxidation of these nitrogen at very high temperature, That's what is causing thermal NO and prompt NO. Whereas if you look at the fuel NO, the source for fuel NO is fuel itself. That's why it's called fuel NO. Fuel consists of nitrogen to a very low level. Gasoline, it is nothing. The nitrogen present in gasoline fuel is nothing. In diesel, nitrogen is present. But if you look at the concentration of nitrogen present in diesel, it will be less than 0.1%. Nitrogen present in diesel is less than 0.1%. Now you can imagine the contribution of this to the total NO. It's going to be negligible as indicated here, because the concentration of nitrogen in the diesel fuel is very low, less than 0.1%. But one thing you need to note down here is, unlike thermal NO and prompt NO, the nitrogen present in fuel is highly active. It can oxidize at very low temperature compared to the oxidation of nitrogen in air, which needs very high temperature to form NO. The nitrogen present in fuel can oxidize and form NO at very low temperature. Okay, fortunately, we have very little NO present in the fuel. That's why we avoid excessive NO formation from the fuel source. This source is negligible due to less nitrogen contained in the fuel. Otherwise, the problem is the nitrogen contained in the fuel is very active. It can quickly form NO at a very low temperature. Okay. So this is due to fuel-bound nitrogen, which is less than 0.1%. So these three are the routes, NO formation routes. So NO is getting formed through these three different routes. Out of this, thermal NO is significantly high. Now let us look at how thermal and prompt NO formation is taking place, what mechanism is involved. So we are starting with thermal NO mechanism. Thermal NO mechanism is governed by these three simple reactions, as chemical reactions, as shown here. In the first reaction, you could see that there is a O radical that triggers dissociation of nitrogen. Nitrogen is very stable. Nitrogen consists of triple bond. That's why molecular nitrogen is very stable. It cannot form radicals easily. That's why this is also called inert species. Nitrogen is one of the inert species, very stable molecule, nitrogen molecule, because it consists of triple bond. Now, if you have to form radical from this nitrogen, stable nitrogen, you have to provide a very high activation energy. Very high activation energy is required to form a radical from a stable nitrogen molecule. That is what is happening in chemical reaction 1. The presence of oxygen radical triggers dissociation of nitrogen at very high temperature. This is an endothermic reaction. What is an endothermic chemical reaction?
Which consumes heat.
Heat, absorbs heat. Exothermic, combustion is exothermic, that releases heat. Endothermic is just opposite. It absorbs heat. So when sufficient temperature is available in the cylinder, this reaction 1 will start, which is an endothermic reaction. It starts with having an O radical, and O radical is available at high temperature. So at high temperature, when O radical is available, it triggers nitrogen molecule, stable molecule, to undergo dissociation. So due to dissociation, you could see that N radical is formed, right? And the other N combines with O and form NO. So there is a formation of NO happening in chemical reaction 1. Okay, that is, so we can say that there is a dissociation of nitrogen in air at high temperature. Okay, once dissociation of nitrogen happens, once N radical form, radical is highly active. The subsequent reaction 2 and 3 will take place so quickly, and 2 and 3 are exothermic reactions. These two reactions are exothermic. They happen so quickly, unlike the first one. Okay, because you have an N radical that is available, which is very active. This N will combine with oxygen. There will be excess oxygen available, always available in a diesel engine. Okay, in SI engine also it's available. This N combines with O2, and you can see that it leads to further formation of NO and a O radical. This O radical helps in triggering into chemical reaction 1. Okay, this N can also combine with OH radical. This is very well available in the cylinder at high temperature. This NO formation again happens with N reacting with OH and forming a H radical. So these three reaction steps are called extended Zeldovich mechanism. Zeldovich is a German scientist who discovered this. Although it looks simple, this is extensively used in combustion prediction, CFD codes, as well as So there are several other additional reactions being developed based on this, but these three are the source or the origin that captures very well the NO formation mechanism in IC engine. Okay, so it's one of the most widely or cited this reaction mechanism in any CFD modeling. Okay, the Zeldovich is a German scientist who developed this. Okay, so the credit goes to him in capturing or modeling how the NO formation is taking place in IC engine, and the contribution of this, as I said, is around 90%. So out of this three reaction, you can say that the first reaction is what is the rate controlling reaction, because unless otherwise you have end radical available, reaction 2 and 3 is not going to happen. So it's all based on the availability of end radical, that is reaction 1, and reaction 1 can happen only at high temperature. Typical temperature is around 2000 K or above. So if you are able to control engine operating temperature below this, you can completely bypass or avoid the formation of NO. Later on, I am going to discuss about the pollutant control strategy. But before that, you keep an eye on this mechanism, because understanding this mechanism will help you to devise a control strategy for minimizing this NO pollutant emission. So I will discuss about the strategy that we are currently doing in our lab to get almost zero level of NOx. So the primary factor is temperature. If you are able to control engine operating temperature below this range, then you are going to get almost zero level of NOx. So high temperature is a primary factor for forming NO in the engine cylinder. You can say that this reaction 1 is a rate controlling reaction, because reaction 2 and 3 are based on the N availability. N availability is based on reaction 1. The second one is prompt NO. Prompt NO formation is happening within the flame. This is what I said. The mechanism involved are shown here. What will happen within the flame? You have this hydrocarbon or carbon radicals available. This hydrocarbon or carbon radical, the source is fuel. When fuel dissociate, it is going to form this different radical. You know, during kinetic, the stable molecular structure is broken down and radicals are formed. So within the flames, you will have a high level of the CH radical, CH2 radical, C radical. These are available within the flame zone. Flame zone is nothing but chemical reaction zone. So within this, you have these radicals available. Okay. So this CH or CH2 or C, what these radicals will do is they will combine with nitrogen. Nitrogen is available at a higher concentration because we are combusting with air. Air consists of 79% of nitrogen by volume, as we have discussed. So you always have nitrogen availability in the engine cylinder, including the flame zone. This radical within the flame will react with this nitrogen and form some nitrogen containing intermediate compound. This HCN or CN are called intermediate compound containing nitrogen. Okay, when CH and N2, for example, if these two react, it is going to form HCN plus N. CH2 with N2, it react form HCN NH. C and N2 form CN and N. So these are some nitrogen containing intermediate compound. This nitrogen containing intermediate compound, what it will do is it is going to oxidize with O and OH. O and OH are also available in the engine cylinder within the flame zone. Okay, so this intermediate compound react with O and OH and form NO. That is how NO formation is taking place within the flame zone. Okay, it all starts with this radical reacting with the nitrogen, forming intermediate nitrogen containing compound, and they get subsequently oxidized to NO through reactions with O or OH. But the contribution of prompt NO is less, as I said, is only 10%. Can you think of some reason for why the contribution is very low? It's only 10%. So the reason here is the flame. I said the NO, prompt NO is the NO formed within the flame region. The flame, thickness of the flame is very low. It's generally around 0.1 mm. 1 by 10, 1 by 10th of mm. Okay, 1 by 10 mm. That's a typical, so the flame is going to be very thin. Why it is very thin? Because of the pressure, prevailing pressure, engine combustion chamber is being subjected to high pressure. Due to that high pressure, the flame is too thin. Size is around 0.1 mm or so. Because of this very thin film, the residence time is the time available for a chemical reaction to happen. There is something called residence time. Since the flame is too thin, the residence time for the chemical reaction or the time available for the chemical reaction to happen and form NO is going to be too short. Okay, this is the reason why the contribution of prompt NO, that is the NO form within the flame zone, is going to be less. You have a very thin flame, short residence time that leads to very little contribution from this particular source to the overall NO. Okay, it's time up. I stop here. If you have any questions, I can take your questions. Okay, so there are no questions. So come prepared for the exam, Saturday's exam. If you have any doubt, you can write to me. Okay, come with your calculator for the people who are taking exam in person. I will provide the answer script. The mode of conduct is exactly same as how we have done for quiz 1. We will have the exam in the diesel hall, 10 o'clock Saturday. For online exam, people who are taking online, those 3 people, Raujan, Yadav and Ramanand, right? So you can, you should have a answer script with you along with the calculator, and you have to come online. I will send the question paper few minutes before the exam. Once you are done with the exam, scan your answer script, send it with your file name as a, with your roll number as a file name. Okay?
Okay, sir.
Sure,
Other
sir.
questions related to the exam?
Sir?
Questions
Yeah.
related to
Yeah, are there any questions?
No, sir. We are preparing it, sir. Whatever you thought.
Okay, fine. Okay, prepare well. And in between, if you got any doubt, write to me. I will get back.
Sir, I have a question. I'm sorry. I just realized little late.
Okay.
Can I ask if you allow me?
It's not too late. Still, I'm here, so you can go ahead and ask.
Sir, one thing I want to ask is basically, suppose we have a SI engine and a CI engine.
Okay.
Now, to get the, suppose for a specific power, like what I mean to say for this BAP level, what I mean to say for the given output, whether the size of CI engine will be more or SI engine will be more.
CI engine will be more.
C engine.
That is because of we are burning it lean, right, sir? That is the only reason.
That is because we already discussed, right? That is because why CI engine size is more. The major reason is you use XSR, 30 to 50% XSR. SI engine run close to stoichiometric condition, meaning you use whatever air proportion you want, you are using exact proportion. Stoichiometric proportion is 14.7 or something, right? Around that number. So that is 14 kg of air for each kg of fuel, typically. Okay. So SI engine, you run close to stoichiometric. CI engine, you always run with XSR. 0.4 to 0.8 is a phi value. So in terms of air mass, the excess air mass goes up to 50%, 30 to 50%. Okay, so you can multiply 14 kg for 1 kg of fuel in SI engine. In CI engine, 14 kg plus 0.5, 14 is 21 kg. So you need more air, you need to store more air. So the capacity, displacement volume has to be high for diesel engine for the same power output. The problem is a heterogeneous mixture. If you start to increase the global value beyond 0.8, the soot value or particulate value is going to shoot up. It's going to be very high. It will become uncontrollable. Even with your after treatment device, you cannot control. So the limiting factor here is the soot for diesel engine design. So you are forced to use up to 50% excess air because of this reason. So the capacity or the size of the engine has to be high. This is one reason. Second one, the compression ratio is high. So the mechanical stresses are high. So the engine has to be heavy to withstand the mechanical stresses. Compression ratio is 2 times higher compared to SI engine.
So can I say that, sir, that BAP of the CI engine will always be lesser than SI engine?
Exactly.
Okay.
DMEP of SI engine is always high because VD is low, capacity is low. BMEP or IMEP is based on work by volume, right? The displacement volume. Displacement volume is less for SI engine for the same capacity, same rated power.
So is that the reason, sir, that homemade generators are made generally in SI engines?
Yeah. It's very small, compact, portable. That's why it's very difficult to design a two-wheeler motorcycle powered with diesel. Although fuel cost is less, okay, so the size cannot be compact.
Thank you, sir. It's clear now, sir.
Yeah, okay,
Thank
fine.
you so much.
Okay, come prepared for the exam and do well. So I would expect a better performance this time. Okay, I will ensure that you have sufficient time available for writing. Also, don't write too much of descriptive things, okay, which is not at all required. Answer up to the point. That is enough. I will just check whether you capture the concept correctly or not.
Okay, sir.
We'll try our best, sir. Thank you so much.
Fine. Thank you. All the best.
Thank you, sir. Thank you.
Thank you, sir.
Bye.